Welcome to myprojectbuzzer.com. Here in this paper we discuss about novel high step-up DC to DC converter for distributed generation system. The power supply voltage aggressively scales with each technology generations, making the delivery of the high quality supply voltage to non-sensitive circuit blocks highly challenging. The number of voltage domains within an integrated circuit is increasing to satisfy stringent power budgets. The increase in the number of voltage domains requires new techniques to generate this voltage close to the load circuitry while occupying a small area. Classically, power supplies occupy large on-chip area and therefore not appropriate for point of load power delivery. Several topologies are commonly used to generate on-chip DC voltages. These DC-DC converters are generally used as on-chip power supplies in high-performance integrated circuit. Conventional DC-DC converter can be grouped into three primary categories: switching, switched capacitor, and linear DC-DC converter. As a consequence of placing these components off-chip, significant voltage drops and bounce are produced at the package level due to the parasitic resistance and inductance between the off-chip components of the voltage converters and the integrated circuit. Additionally, the parasitic internal connector impedance between the discrete components of the voltage converter can produce significant power loss. Furthermore, with power supply scaling, analog and digital circuits are less tolerant to fluctuations in the supply voltage. A DC to DC converter is an electronic circuit which converts a source of direct current from one voltage level to another. It is a class of power converter. DC to DC converter are important in portable electronic devices such as cellular phone and laptop computers, which are supplied with power from batteries primarily. Such electronic devices often contain several sub-circuits, each with its own voltage level requirements, different from that supplied by the battery or external supplies. Additionally, the battery voltage declines as its stored power is drained. Switch to DC converters offers a method to increase voltage from a partially lowered battery voltage, thereby saving space instead of using multiple batteries can accomplish the same thing. Most DC-DC converters also regulate the output voltage. Some examples of extensions include high-efficiency LED power sources, which are a kind of DC-DC converter that regulates the current through the LEDs, and simply charge pumps, which double or triple the output voltage. Here in this paper, we propose a novel high step-up DC-DC converter for distribution systems, which are proposed to utilize the two capacitors and one coupled inductance to optimize the regulated output voltage and sizes of the internal circuitry. Now I am going to discuss about flow diagram of our project. In the first stage of our flow, we give the input in regulated DC supplies to our converter stage. Here it gets the controlled DC output at the load by using the feedback loop. From the feedback loop, it gets the controlled pulses generator to activate the switching devices in the converter circuit. To activate the switching devices, it gets the error signals which are generated from the input unregulated DC source and from the converter output at the load side, and this error signal was fed first to the error amplifier. At the output of error amplifier, it gets the controller output. In the controller stage, it gets the error amplifier signals and provide controlled signals to comparator input stage. In the comparator, it gets the controlled signals of error signal and it compares the signal with the reference signals which are given at the another side. Then this compared output will generate the pulses which need to trigger the switching devices in converter circuit. From the switching devices of the converter circuit, it gets regulated DC output and regulated load supply output. This was also feedback to the feedback loop and gives the controlled signals to DC to DC converter circuit. Our output will generates boost converter, that means step up converted DC output. This was fed to the output high voltage DC usage source. Here we give the input as low voltages. For example, we give 200 voltage as an input and gets us 400 voltage as an output. Here the power factors of our output circuit was maintained at nearly 1, which will generate there was no any errors or errorless circuitry. According to the power factors, we can estimate our overall architecture's efficiency in power system. Now I am going to discuss running procedure of our project. Here we design the overall architecture designs of our proposed step-up DC-DC converter to regulate the unregulated DC inputs to regulated DC output at the load side. Here at the initial stage we give input as unregulated DC input and this was regulated and supplied to load side by using the internal switching devices of our controller architecture. To activate the switching devices, we provide a feedback loop to give the control signals and generator pulses which are generated to activate the gauge terminal of our switching devices to regulate our DC input. According to the switching speed, it will generate and fine regulated output will be produced at the output side. For that reason, the controller will generate a high speed pulse generated output according to our error signal which are produced at the load side. The error signals was occurred by using the previous stages of error. According to the previous stages of error, this error signals was fed back to the error amplifier to amplify the error signals to an overall amplifier range. From that error amplifier signal, the comparator checks the reference signals on the error amplifier and it will generate the pulse output to activate the switching devices of our DC to DC controller circuit. Then finally we generate regulated DC output for the unregulated DC input circuitry. Thus we got step up unregulated to regulated DC to DC converter. Thank you.